Good morning. This is Dinesh, CM, Assistant Professor, Government First Aid College and PG Center, Chintamani, Karnataka. Today we shall study about the transistors under semiconductor physics for BSc students of final year who study in their physics stream. And you can see at the corner to the right side there is a picture which shows that it is a replica of first working transistor which is invented in 1947 by Bardeen, Walter and Shockley at the Bell Laboratories of United States of America. Here it shows that there is a first connection, second and third, maybe probably emitter, base and collector. And this is a novel invention of 20th century. We will study what is its construction, what are the features, how the current will get carried, how to bias this, all these things about a transistor we will study for this session. And a student should have a prerequisites about the basics of a p-type semiconductor and n-type semiconductor. We will get a p-type semiconductor when an acceptor impurities like a trivalent impurities like a trivalent materials like gallium, boron, indium, aluminum, etc. are doped with pure silicon or germanium. We get a p-type of semiconductor when a donor impurities or a pentavalent materials are doped with a pure silicon or germanium, we get an n-type of semiconductor materials. Example for n-type of semiconductor materials are phosphorus, arsenic, antimony, bismuth, etc. are doped with a pure silicon or germanium, we get an n-type of semiconductor materials. And this p-type and n-type semiconductors are said to be an extrinsic semiconductor materials. When joined together, at the point of joining there is a formation of a junction, and this junction is called as a p-n junction. And this formation of p-n junction is a prerequisite for any student to learn about a transistor. And this p-n junction should be forward biased or reverse biased depending on the type of connection of a battery to a p-n junction. When a positive of a battery has connected for a p region of a p-n junction or a p-n diode you can call, or a negative of a battery has been connected to an n region of a p-n junction, that is said to be, the p-n junction is said to be under forward biased condition. In other words, that is p region has been connected for n of a battery, negative of a battery, and n region has connected for positive of a battery. The biasing of a p-n junction is considered to be reverse biased. And the one should know that the biasing characteristics of a p-n junction before coming for the study of a transistor. And a student should also have an initial idea about the type of carriers, that is the carriers are of majority type or a minority type. Majority charge carriers, in case of a p region, the majority charge carriers are positive charges or a holes. In n region of a p-n junction, the majority charge carriers are electrons. And the creation of an electron hole pairs. So how do this electron hole pairs will get created when a p-n junction is applied for an biasing? One should know that how that charge carriers will get generated. Not only in p-n region or any junction regions, under applications of high potential or high temperature or high energy, the bonds will get broken up. There is a formation of charge carriers thereof, the electron hole pairs. So these are all the prerequisites. With these prerequisites, after this session, one should be able to understand the types of charge carriers, that is the charge carriers are of electrons or holes, and different types of transistors, for example bipolar junction transistors, or of two types, one is NPN and PNP transistors, and their circuit symbols. The circuit symbol is different from the physical representation of a transistor. So that difference between these two, a student should be able to learn from this session. And the transistor regions, there are three different regions of a transistor, that is emitter, base and collector, and their construction, what are the doping concentrations, how they are doped, how they are joined together. So that thing a student should be able to learn. And a transistor biasing, unlike an PN diode, a transistors can be biased in a forward and reverse ways. So when in a different regions, or an emitter based junction can be forward biased, or collector based junction can be reverse biased, depending on the applications, one should be able to bias a transistor, and how it should be biased in order to function a transistor as an amplifier or as a switch or any other particular applications, how it should get biased, that a student should be able to understand. And a student should also able to learn about different currents. What are the emitter current, what is a base current or a collector currents, one should learn in this case. And this is in different currents how it is getting, and how are the different terminals, and what are the different terminals of a transistor. So let's see that these are all the learning outcomes. In addition to this, like how a transistor will get connected in case of an different functions, or a common emitter mode, common base mode or common collector mode, different modes of connections can also be understood after this session. And coming to the basics of a transistor is a three-terminal, two-junction electronic device. It is a three-terminal, two-junction electronic device, and it is generally made up of a pure silicon material which is doped with an impurities. Now, what is the word called as a doping? A doping is an introduction of impurities to a pure silicon material for the purpose of a modulating for optical, electrical or any other structural properties. To modulate the optical, electrical and structural properties of a semiconductor material, one should dope a pure silicon or a germanium material, and after this doping the material is considered to be an extrinsic semiconductor materials. So as I said that, like PN diodes, the semiconductor transistors or transistors are a most popular semiconductor devices. It is a device. I said that it is a three-terminal, two-junction electronic device. It is used for a particular purpose. An example are bipolar junction transistors, BJTs, the term generally it is referred. And there are different types of devices like bipolar junction transistors, as I said, field effect transistor FET. In FET there will be multiple FETs are there, field effect transistors, called as in junction field effect transistor JFET, and there are N channel and P channel negative, electron carried junction field effect transistors, and holes carried junction field effect transistors, or metal oxide semiconductor field effect transistor termed as MOSFETs. Like that there are huge devices, that let's concentrate more on these BJTs for this session. And these transistors are said to be most significant invention of 20th century. Whatever it has been invented earlier, unlike lasers which has been invented, like that many other materials. So this is an important invention of 20th century. So these transistors, why it is an important invention? Because they are the building blocks of digital revolution. These transistors are the building blocks of digital revolution. And these transistors can be used in many ways because of its complex structure. The transistors are more complex and they can be used in many ways. Why they are more complex, we will come to know in this session only. The most important feature of a transistor is that it can amplify signals. Whatever the signals you are feeding, this is a symbolic representation of a transistor which has a base, emitter and a collector. For this base you are feeding an input. So this is a signal you are feeding into the circuit, and this signal will get amplified. Amplified means the voltage of the input will get increased. You can see that there is a half cycle. The amplitude of a half cycle has been increased. So this is an output. The voltage gain has been taken place. In addition to this voltage, there will also be a current gain. And also, if at all I want to invert a signal, I can get a signal inversion with the help of a transistor. And it can also be act like a switch. So this is a particular application of a transistor. So the different regions, you see that there is a collector and emitter region can act like a switch by controlling a suitable voltage or current across a base. So it can act like a switch, it can act like an amplifier. The amplification means by making a weak signal into a strong signal. For example, a sound in feeble sounds can make louder, and the signal levels could be greater. And in general, a transistor will provide a function which is called as a gain. I can get a current gain, I can get a voltage gain. As I said, this is a special advantage of a transistor. And these BJTs do carry the two types of carriers. It could be holes, it could be electrons. So the two types of charge carriers in BJTs take part in current flow, hence the name bipolar. The name bipolar is because it has two types of charge carriers. They are holes and electrons. And it has an BJT is a three-terminal device. It could be of an NPN or PNP transistors. So it has an N region and P region. And N region, in case of an N region, it consists of the negative carriers or free electrons it carries. And in case of a P region, it has an positive carriers or a free holes. Holes can move from one region to the another region. They are free to move. And in case of bipolar junction transistor, they are of two types. One is PNP transistor and NPN transistor. So PNP means an N region or an N type of semiconductor has been sandwiched between the two P type of semiconductor regions. And N has been sandwiched between the two P regions. I will get PNP. Or in case of an NPN transistor, a P type of semiconductor has been sandwiched between the two N type of semiconductors, so that I will get NPN. NP N semiconductor I can get. And this is something about the different regions and different types of bipolar junction transistor. And each transistor, as I said, it has three terminals. These three terminals are called as an emitter, base and collector. So I'll show you a diagram. This is an three terminals. This is called as emitter, base and collector. So this forms an PNP, an N region which has been sandwiched between the two P regions, which will gives you a PNP transistor, and one terminal considered to be emitter, another is base and another one is collector. Similar to this, there is an NPN transistor. P has been sandwiched between the two N regions. And now let us see what is this emitter, what is this base and collector. An emitter is one which will send the carriers into the base region and then to the collector. So the main function of an emitter is to send the carriers into the base. What do this base do? The base acts as a control. It will control the charge carriers. That means it can allow none of the charge carriers to move through that base, or it can allow some carriers to move through that base, or it can allow many charge carriers to flow through the base. That means the base is acting like a controller in case of a transistor. It is very analogy or very identical to that. When water is moving in a pipe, for that pipe you are fixing a tap. So tap will act like a controller, and after that moving through the tap, the charges will move outside. The charges which are moving outside, which will be getting collected, or a water is getting collected, which is the water is identical to the charges. The water which is moving in a pipe, before this tap, the region is considered to be emitter, which will supply the charge carriers. The tap will act like a controller. So that means it can control. It can when you tighten the tap, no water will flow. When you release some tap, a controlled water will flow through that. When you completely release the tap, all the water which is coming out from the emitter, it will move to a collector. It is acting like a tap in case of a water flowing through a pipe. And similarly, in case of a transistor, emitter, base and collector regions, the charges could get controlled in the base region. And this is considered to be a collector. The collector collects all the charge carriers which is coming from the base region. And this is a typical structure of an PNP and an NPN transistor. So as I said that it has three regions. And the one which is there at the middle represents the circuit symbol for a PNP transistor and an NPN transistor, which has three terminals. This is a collector terminal, base terminal and an emitter terminal. And this is for a circuit symbol. You can see that there is an arrow on the emitter region. The arrow on the emitter region will shows the direction of current flow in a transistor. So when an arrow is shown inside, the direction of carry of a majority charge carriers. So here the charge carriers are holes, and here the charge carriers are electrons that are moving out towards the majority charge carriers are moving outside. Here they are moving inside. We will come to know later during the explanation. And also the picture indicate that this current is flowing outside, which constitute an collector current, which is having a typical units of milliampere, and this current is flowing out. And there is an emitter current IE, which is again in milliampere, so the current is larger. And in case of a base current IB, which is in microampere, the current is very low, that is 1000 times less compared to the collector current. And these arrows indicate the direction of current flow. Similarly, in case of an NPN transistor, except this arrow, everything else is get reversed because of NPN. Direction of current flow will get reversed. So this is an collector current IC, base current IC, and emitter current IC. The direction of current flow will get reversed. And let's see how this construction of an NPN and PNP transistor will take place. As I said earlier, it has a 3 doped regions, NPN, 3 doped regions, and it has an NPN and PNP types. So both NPN and PNP types has an narrow region, very narrow region, which has been sandwiched between the larger regions of emitter and collector. A narrow region has been sandwiched between the larger regions called as emitter and collector. A narrow region is considered to be a base, and this is a physical representation. And coming into the regions, what is the thickness of the different regions, what is the doping concentrations, if at all we want to study the emitter region. The emitter region is an heavily doped one. You can see that there will be a lot of negative charges which are present here. And its job is to emit the charge carriers into base. So this emitter region, which is heavily doped, larger number of negative indicates the dopants which are added will be larger. For example, in case of a pure silicon, there will be an 10 power 23 atoms will be there for an 1 mole. In that one, about 10 power 1 in 1 lakh, 1 atom in 1 lakh, that means about 10 power 18 negative charge carriers will be added to the emitter region. And this base region, which is a very thin region, and it is lightly doped with an P type of impurities. So its impurities will be very low. For example, 10 power 12 positive charges which have been added. 10 power 12 trivalent impurities. You can add an trivalent impurities like boron will be added, gallium, indium, aluminium, gold, etc. can be added to the base, a trivalent impurities. And in case of a collector region, the collector region, the collector is lightly doped, and its thickness is very large compared to the base and an emitter, because it has to collect all the charges which are coming from the base. For that purpose, its area will be larger, or its region or thickness will get increased. And this is moderately doped. This is heavily, this is lightly doped, and this is moderately doped. Compared to the emitter, this is lightly doped material with a N type of impurities. And this is larger of the other two types, or about the all three regions. The collector region is a larger region. And coming into the doping concentrations we have studied now. Now coming into how these regions will get connected. A transistor is having a 3-terminal device. For any operation, we need an input terminals and an output terminals. For input, we need 2 terminals. For output, we need 2 terminals. Totally 4 are required, but we have only 3 regions of a transistor, or a connecting ports. We have only 3. So one should be common for both input and output. So depending on this common connections or a common configurations, we can have a 3 different types of configurations. I can make a base as a common, emitter as a common, or a collector as a common for both input and outputs. So depending on that, I have the 3 different configurations. First, let us see the common collector configuration. Here we are making the collector region is a common for both input and output. Here base collector region is it acts like an input, emitter and collector acts like an output. The input signal is applied to the base terminal. That means about these two terminals the input will get added and it is taken out at the emitter region. That will give you an output. That is the one configuration. The second configuration is common base. Here the base is common between the input and the output, and the base terminal is common for both input and output, and it is not applicable for amplifier. This is a special feature of a common base configuration. Why? Because the relation between the input current gain IB and output current gain IC is approximately 1. The ratio of output to the input, if you take, you will get only 1. Therefore, it cannot be act like an amplifier. So for an amplifier, it should be larger than 1. If it is output is 2 and input is 1, the gain is 2. Ratio of output to the input. Any units you can take, milliampere or microampere. And it's a ratio again. In that ratio, the units will get cancelled. The ratio, the resulting will gives me a gain. And in case of a common emitter configuration, the input is base emitter region and output is collector emitter region. Here the emitter is common for both input and output. And this common emitter configuration is mostly applied for all practical amplifying circuits because it has a good voltage gain or a current gain or a power gain. So it has a very good gain in this configuration, hence it is most commonly used circuit. The other one can be used for a switches and this can be for amplifier. Hence the different modes of combination, different modes of configurations will be helpful. Hence I said that it is most complicated functions. So it will do complicated functions. Almost all of the integrated circuits are building blocks from these transistors. So the about a one integrated circuit will have a million number of transistors. So when a transistor is in the on case or it is in the off case, I can make a transistor to act like a ones and zeros. And if you use a multiple ones and zeros, it can be used for coding or decoding. It can be helpful for that purpose. So in transistor bias, let's go for a different biasing. As I said that unlike an PN junction it could get biased, we will see this transistor slowly one by one. A transistor is having a collector base junction, base emitter junction. In case of a collector base junction, when it is under reverse biased means this is negative region and positive region. Positive region has been connected for negative of a battery. This indicates a battery and this indicates the current, how much it is flowing through this. So the negative of a battery has been connected for positive of a junction, positive region of a junction, and negative of a junction has been connected for positive of a battery. The PN junction which has been formed here is said to be under reverse biased condition. What is reverse biased here? Collector base junction has been reverse biased. And because of reverse biasing, the PN junction or a depletion region, what you call, it will get enhanced. A depletion region is what you call, the depletion region is an resistance region. Because of opposite polarity which has been formed there, it acts like a resistance region. When the reverse bias is applied, depletion region will get enhanced. So more resistance for the flow of current through the junction will offers, hence there is no current will flows. The meter reads there is no current is flowing here. So this is something about the reverse biasing of a collector base junction. Let's see if the other junction is getting forward biased. Under forward biasing means this is a battery and this is a positive region of a junction. Positive region is connected to positive of a battery. A negative region has connected for negative of a battery. Because of the negative and negative, there is a repulsion between these two. The PN junction will get narrowed. PN junction is narrowed means low resistance for the flow of current. Hence, most of the current will flow through the junction. Whatever the current which is coming out from this battery, the potential, it will leads to flow of charge carriers through the PN junction. Hence, you can see there is a large current which is flowing through the PN junction. So we have come to know that under reverse bias condition, no current flows. Under forward bias condition, large current flows here. And now let's see when both the junctions are biased. How they are biased? CBE is reverse biased and BE is forward biased. And under this biasing condition, you can see the current flows everywhere. That means there is an across the collector region current flows, it will constitute a collector current. Across a base there is a current flow which constitute a base current. Across an emitter there is a current flow which constitute an emitter current. And one can see that base current is small and collector and emitter currents are larger. So when both of them are biased, current flows everywhere, but base current is low, collector and emitter current is larger. Because of biasing, this you can observe here. So by controlling an current through the base, you can control current through the collector and emitter. We will see that now. So here, when you supply a very small current through the base by adjusting the voltages across in voltage sources, you can control a base current. So if base current is very low or if it is zero, then you can see that the collector current is almost zero and emitter current is zero. When a small amount of base current is flowing, you can see that there is a large current flow through the emitter and collector. Hence, base current act like a controller of a current flow in a transistor. When switch open, our base current is 0, all currents go to 0. So IB controls IE and IC. So you can see that the gain, you can study the gain is something small controlling something large. So if a very small IB in case of microampere and current across a collector is in case of milliampere, gain will be 1000 times. Hence, in order to have a better gain, one should have a very small base currents. And the current gain from base to collector, let us see as an example. Here, the emitter is the one which will gives the charges for a transistor. That means for a base and collector, if it is giving a 100 milliampere and the base region is having an opposite polarity, about 1 milliampere, it will getting recombined. It will constitute a base current. And remaining 99 milliampere will be collected by the collector, which constitute a collector current. So the ratio of output to the input, what is an output? The collector current. What is the input here? The base current. You are feeding into this. Hence the ratio 99 divided by 1 milliampere will get cancels. The remaining will be 99. Hence the gain is considered to be 99. What is gain? It is indicated by beta, the term which is called as an current gain. We generally call common emitter current gain. We call across this beta 99 by 1 which is equal to 99, which is considered to be the collector gain, ratio of output to the input, which will constitute, which is an important parameter. And applying a loss, the loss for a transistor you can apply a Kirchhoff's current law. Across this junction, how many number of current which is coming out from the emitter, which will be equal to the current which is recombining and the current which is flowing through the collector. Hence I can call IE, supplied current, which is equal to the current which is getting recombined at the base and the current which is collected across a collector. So 1 milliampere plus 99 will gives me the 100 milliampere, which is equal to the current which has been supplied by the emitter. How much of the carriers will get generated across the emitter can be calculated by using IB and IC. So hence Kirchhoff's law is applied for this transistor circuit. And earlier till now we have studied an NPN transistor. If you make in the other way for a PNP transistor, how holes flow from emitter to collector. So here all the phenomena are same except the polarities will get reversed. So in case of an biasing, you can see IE is 100 milliampere, IB is 1 milliampere and IC is 99 milliampere. Everything else is same, only the polarity directions will get changes. That means the holes flow from emitter to collector. Other than that, there is no difference. And now we will see what are these NPN and PNP biasing, how they are getting different. As I said earlier, the fundamental operation of an PNP transistor and NPN transistor is similar except the role of electron and holes. Earlier, the electrons will get used to flow from emitter to base and then collector. Now in case of a PNP, holes are moving. So that means the role of electron and hole flow or majority or minority will come to know. And voltage bias polarity, you can see this is a region, this is an NPN transistor. For NPN transistor and for an PNP transistor, the type of biasing will get reversed. This is also very, very important. That means here N region has been connected to N, P has been connected to P. That means this is under forward biased, and N has been connected to negative, positive region of a battery is connected to negative region, negative of a battery has been connected to positive of a transistor region. This is said to be under reverse biased for an amplification of an NPN. And here P is connected to P, N is connected to N, which is again forward and reverse. The polarity of a batteries are changing, polarity of a transistor is getting changed. That should be observed. And current direction is also important. Here the majority charge carriers are moving towards the emitter region. The majority charge carriers are moving from emitter region towards the transistor, towards the base region. The majority charge carriers are moving. The direction of current flow is also changes when both types of transistors are changed. And in this session we have been studied the basic idea of significance of transistor for a day-to-day life and structure of an bipolar junction transistor, types of charge carriers, electrons and holes, and transistor biasing and operation, and transistor circuit configurations. These are all some of the outcomes from this session. So we have studied the transistor structure and its circuit symbol, basic construction, which are all the majority charge carriers, minority charge carriers, and doping concentrations, and which is the narrow region or a thin region, thick region, and a region of a larger area region. Collector is in larger area, base is in very thin, and emitter is in moderately thin. The doping concentrations also we have studied, and which are the majority minority charge carriers, how to bias, and what are the operations, and what are the configurations or a circuit configurations we have studied. These are all the session outcomes. And for references you can study typical books which are considered to be in from considered for this presentation are Basuraj Sadashiv, which is a prescribed book for 5th semester published by Omkar Publications, and some of the internet sources have been used. And also you can use a very good book that is from Murugesan and Shiva Prasad of Modern Physics, 18th edition, S. Publishing in the year 2017. It has a series, you can refer to them. Thank you for your kind cooperation for this listening. Thank you, one and all.